Okay. So from today, we will review what is the deep learning. Okay, and also spending few hours, we will spend what is the deep learning and their CNN architectures and how we can implement some basic deep learning architectures in PyTorch. Okay. Okay, so in previous lecture, I already told about this ImageNet challenge. Okay, this is the largest ImageNet, I mean the computer vision data sets, which is intended for the image classification task. Okay, in that task, the images are given, and our aim is to classify those images according to their main object. Okay? So we are somehow assuming that there are only one object inside the image. Okay? And our aim is to classify images depending on the main object. And this is also the graph I already showed to you. Okay, so the x-axis is the year, okay, and y-axis is the error rate of the state-of-the-art algorithm in that year, proposed in that year, the winning algorithms. And you have to notice that I don't know why two cursors are shown. I don't know. Okay, it's now okay. In the early years, early 2010s, there was the shallow learning algorithms, which I mean was the state-of-the-art algorithm in machine learning domain. And we are actually applying some support vector machine, which is often called as the SVM. And also there are some human engineered features. Using their human engineered features combined with SVM, we classify the images, okay, for the ImageNet data set. And their error rate, state-of-the-art error rate was like 28 or 25%. So when given 100 images, the algorithm tend to be wrong for the quarter of the entire images. Okay. So we call that algorithm as the shallow learning algorithm because those algorithms are only having one layers. Okay. But the year of 2012, the AlexNet, the first successful CNN architectures was proposed in the New Reefs conference. And that architecture is having 8 layers. Okay, so after this, because the architectures are having more than one layer, we are calling those architectures as the deep learning algorithm. Okay, and you can see there was huge gap between the algorithm for deep learning and shallow learning algorithms. And after that, people try to improve that AlexNet architecture proposed in 2012. And gradually, they are tending to uh, make the depths of the deep learning algorithms larger. And you can see 8 layer, 19 layer, 22 layer, and 152 layers here. Okay, so the research trends are like to increasing the number of layers in deep learning architectures. And also you can see their error rate is gradually reducing. Okay. And the rightmost, you can see the human performance in this ImageNet challenge. Even humans are sometimes confused because for some images, humans even not familiar to that object. So even humans are wrong for when 100 images are given, they tend to be wrong for 5 images. This is the normal human error on the ImageNet challenge, 5.1%. But in the year of 2015, the error rate for the ResNet architecture, which is the successful CNN architecture, having more than 100 layers, their error rate becomes more robust than the human performance, okay, recording 3.6% error rate, okay. So you have to remember these two sensational event, okay. In the year of 2012, the first successful deep learning architecture that improves the state-of-the-art shallow learning algorithm by 10% has been proposed. Okay, and in the year of 2015, it surpasses the human performance. Okay, and after that, people are more and more having interest in using the deep learning architecture. And in the year of 2016, even the AlphaGo appears and it wins the professional Go player, right, in Go game. Okay, so this slide is summarizing some difference between the deep learning and classical machine learning algorithms, which is using the shallow learning algorithms. In the first row, you can see the um, okay. In the first row, you can see the classical machine learning algorithm, which is actually shallow, having just one layer. So this is the shallow learning architecture. Okay. Oh, sorry. 이거 Anyway, sorry about this. I don't know why. This is so unstable. think the only way is turning off and turning on again. But I'm turning on off, will turn on again. 예, 저기 프로젝터 관련은 일로 연락을 달라고 하시던데, 예, 106동 T205거든요. 예, 이거 연결이 되다가 그냥 한 번 빠지니까 다시 막 계속 안 되거든요. 한 3시 반에 오시면 좋을 것 같아요. 네, 예, 예. Okay. By the way, I'm curious why this place is only empty. So maybe next time I will give some extra point to the person who will sit here. 여보세요? 아, 예, 지금 계속 안 돼서 지금 T205에 106동 그냥 와주시면 좋을 것 같은데요. 예, I don't know. It works now. Okay, yeah. So actually, sorry about this delay, continuous delay. Maybe next time, we will check this again and maybe make not this happen again. Okay, so the first law is showing the shallow running algorithm. And this is the input image whose size is 224 by 224 by 3. So this is the width and this is the height of the image. And normally we are using the color image. Okay, so the color image means there is a red RGB. I mean, RGB means red, green, blue pixels are there. So when you have the color image, their dimensions are having the three channels. Okay, apart from the width and height array, you have another dimension for recording having the pixel information for the RGB. Okay, so and also each R component, G component, and B component, they are having the values from 0 to 255. Okay, so they are having 8-digit information. Okay, sorry. 여보세요? 또 돼가지고 한 3시 반에 와주시면 좋을 것 같습니다. 예. 이게 됐다 안 됐다 지금 완벽하지가 않아서 다음 시간을 위해서 한 3시 반에 와주시면 좋을 것 같거든요. 이게 빠지면 한 번 빠지면 되게 안 돼서 좀 체크를 했으면 좋겠거든요. 이게 뭐 계속 한 번 이렇게 빠지면은 계속 안 되거든요, 지금. 근데 원래 안 그랬는데 제가 수업 중이라서 3시 반에 와서 얘기하시면 좋을 것 같습니다. Okay, so this is RGB. Okay, so anyways, to represent the color information in the computer, you have to denote R component, G component, and B component for each pixel. Okay, and by combining these three information, the computer is representing the color information of the pix. I mean, for example, in this figure, these pixels, each pixels are having the RGB component, and maybe these pixels are having more blue component compared to the red and green component. That's why we are feeling like that these pixels are more blue pixels. Okay. And from these images having width, height by three channel dimension, we are extracting some features, the human engineered features. Okay, so this is the feature. Okay, a feature that is some vector again. So this is the vector, one-dimensional vector. So this is the multi-dimensional, actually three-dimensional array. The input images are array, but we are actually wanting to extract some useful information from the entire image array. And that is actually the feature. Okay, for example, if we want to do the face detection task, then the color information is one of the most important feature vector. Okay, so the facial color, that is the most important feature for achieving the successful facial detection. Okay, so for each tasks, for example, object detection or facial detection or classification, we have to have designed the human engineered features by ourselves, okay, to deliver successful the accuracy in our targeted tasks. That's the and after extracting the feature, we are using one layer architecture, the classical machine learning algorithms such as the SVM, to map this feature vector to the desired classes. Okay, so for example, in image classification, the output is n-dimensional vector that is denoting n-class probability. Okay, and among this n-class probability, we are choosing the one that is having the maximum value, which is we are thinking that that vector, that entry is having the highest probability. So we are choosing that entry as the image classes, corresponding image classes for the RGB image. Okay, are you guys following this? Okay, that's the classical way of achieving the image classification. But the second law is showing the deep learning architectures. Okay, so the deep architectures are having more than one layers, and they are directly mapping the input images to the output class probability. Okay, so there are actually two merit of these deep architectures. The first one is the humans can miss some of the important feature vector. Okay, so I mean, this is the first merit of the deep learning architecture. The deep learning architecture, the first part of the deep learning architecture, they are somehow automatically learn some intermediate representation for different tasks. Okay, so for humans, even for facial detection, we can mistakenly omit some important features like facial color. Okay, so because inside the deep learning architecture, the yellow components are automatically data-driven manner they are learned. Okay, so uh, in here, because we are using the human engineered features, the humans can mistakenly miss some of the important features, but in these deep learning architectures, the earlier features are automatically learned. So that is more optimal. Okay. That is actually one reason, the first reason why the deep learning architectures are better than the classical shallow learning algorithm by their accuracy. And the second one is non-linearity. I mean, how to say, the shallow learning algorithm, for example, this type of layers, just having just one layer, normally in machine learning, they are representing this type of linear equations. Okay? In Korean, it's 1차 함수. 1차 함수 다 배웠죠? 이거 직선 그래프고 뭐 고등학교 때 다 배웠잖아요. So their graphs are straight line. Okay? When mapping input x to the output y, they are representing only the straight line, the linear relationships between x and y. But when you increase the power of this, the mapping between x and y, it becomes nonlinear and it can represent some complex curves between the x and y relationship. Okay, so we in English we call it as the nonlinear relationship between input and output. Okay, if the function is too simple, we can only represent the linear relationship between input and output. But because we stack multiple layers, the network itself can now having the capability to represent more nonlinear relationship between inputs and outputs. Okay, that's also the other important reason why the deep architectures are better than the shallow learning algorithms. Okay. And also most computer vision applications or some real world applications, they are having data that lying on the nonlinear space rather than the linear space. Okay. So for example, the X point and circle point, if they are separated like distributed like this, that we can have just one straight line that can, how to say, classify these two classes, okay? But normally, in the real world data, the situation is not like this, okay? Always the data space, there's distribution is mixed, okay? So in many cases, we have the data distributed like this, and we cannot simply draw one straight line that can classify these two different classes, okay? This is more realistic situation. And in these situations, we have complex curves, okay, that can classify that can, in more detailed level, describe the boundaries of these two different classes. And these curves can be described by some nonlinear representations, okay? So nonlinearity, if we stack more layers, that architectures having more than one layers are having the capability to represent nonlinear boundaries or nonlinear representations. Okay, that's the other important reason why deep learning works better than the machine learning algorithms. And I will now briefly introduce the CNN architectures. CNNs are abbreviation for convolutional neural network. Okay. So in the year of 2012, the AlexNet, one of the successful CNN architectures, introduced. And after almost 10 years in computer vision research, the CNNs was the prevailing algorithms. Okay. But you have to understand any differentiable layers could be here. Okay, so this is the RGB image having width by height by three-channeled input array. And our aim in image classification is to predict some one-dimensional vector having n dimension, and n denotes the number of classes. So this will denote n classes probability. Okay. So our aim in image classification is to output n-dimensional vector from these RGB image arrays. Okay. And any differentiable layers could be located between this input and output. Okay. Then what this differentiable means is any difference, the layers whose output, let's say the output is y and x is the input, and the parameters are set, let's say it is sector. If given one layer, its output is differentiable to their input, and also their output is differentiable respect to their intermediate parameters. If some layers are meeting these two conditions, we are calling those layers as the differentiable layer. Okay, are you guys understanding this? I mean, when given layer and their layer's output y is differentiable to their initial input, and their output is differentiable to their intermediate parameter sector, if layers that meet these two conditions, we are calling those layers as differentiable layer. And if layers are differentiable, we can train those layers. We can train their parameter sector. I mean, X and Y, the images and their corresponding labels are somehow constant. They are fixed. They are given as the data, right? We cannot change their X and Y, but we can change our network's parameters, okay? For example, in CNN, the parameter sector is the coefficients, okay? I will, re-explain this later. Anyways, let's say this layer as the function f, okay? If we input our initial input image x to this layer f, and whose parameters are sector, this is semicolon, okay? This is the, why the output of function f is outputted from the input x and via the function f having the parameter sector. So this is describing the situation here, right? The only thing we can, change is the parameter sector here. F is also fixed across the training and testing phase of the machine learning algorithms. Only the parameter sector is changes. And sector is at the initial stage that's randomly initialized. It's like a baby. The function f is like a baby. So when baby is first come to the world, it knows nothing, right? So the parameter sector is, you can see there, the baby's brain's parameters, okay? It is randomly initialized, and the only thing he can do is crying, right? Because he knows nothing, right? But by giving some feedbacks from their parent, okay, maybe in the machine learning, by giving some feedbacks from the data X and Y pairs, the parameter sectors are gradually improved, right? The babies, their brain's parameters are gradually improved by some giving some feedbacks from their parent. Okay. If this parameter sector is more and more improved, how they are improved is they are actually given this X, they are wanting to make their prediction Y close to their corresponding ground truth. Okay. In that direction, the parameter sector is improved during the training stage. Okay. And after the training, after the baby is grown somehow, if we give some new input X to the baby or these layers, function f, having improved parameter sector, then he can predict something, some plausible y, the output y, for the unseen x. Okay, are you guys following this? So that is actually the thing we want to achieve in the deep learning or machine learning. Okay. But the important thing you have to remember in this slide is improving sector is possible when layers are differentiable. Okay, if those layers are uh, having the function f, and that function is actually having these two gradient, okay, those networks could be trained, which means the parameter sector could be improved. Okay, okay, and I will say it in more detailed level. So, I mean, the forward rule, when given the deep learning architectures, okay, so this is drawing some deep learning architectures, okay, and this is the input image I, okay. You can, in previous slide, we say the input as the X, but here, because it is image, so we usually use I as the abbreviation for input I, okay, input image. So sometimes we use I or X, okay. So this is the output of the deep learning architecture Y again, okay. So this is representing how the output Y is coming from the initial input image I. Okay, we first apply the layer H, okay, and then apply layer F, whose parameter is sector. Okay, so this is the somehow the mathematical function that can describe how we can obtain the output of Y, the deep learning algorithm's output from the initial input I. Okay. Then we call this as the forward rule because from left to right, how the signals proceed, we can describe it in this formula. Okay, so we are calling that as the forward rule. And the other important thing is the two gradient that I mentioned in previous slide. So this is the differentiation of the output y respect to their input. Okay, so for this function f, uh, I mean, when the function f, the layer f is differentiable, his output y have to be differentiable respect to their input x. Okay, and also this layer f's output y should be differentiable respect to its parameter sector. Okay, so if the layer inside the entire deep learning architecture can meet these two conditions, we can call that layer F is differentiable. And another important thing is if layer H also meets these two conditions, and if layer F meets these conditions, the entire combination of H and F, they are becoming differentiable again by the chain rule. Okay, so I mean, we can see this combination of H and F, okay, as the new function, if H and F both are differentiable, we can see the entire network that combining H and F as the one function, and we can get these two gradients by combining the intermediate gradient for H and F, okay, via the chain rule. Okay. For example, dy di could be obtained by by multiplying these two, right? Okay, and this is meaning uh, that a layer H is differentiable respect to their output X, respect to their initial input I, and this is the differentiability condition for layer F. Okay, are you guys following this? Okay, so via chain rule, we can multiply this kind of gradient for each layer and to make it for the entire layers that those two are combined. Okay, so I mean, we can say it like this: if individual layers of the uh, entire deep learning architectures are differentiable, if all of the individual layers are differentiable, then entire deep learning architectures are again becoming differentiable via the chain rule. Okay. And so, and also ultimately, why this differentiability is important is the thing we are eventually wanting to achieve is this. So this is called as the gradient descent algorithm. Okay, so this is via chain rule is denoting dy, not dy. This is denoting dl dissector. Okay, so if I rewrite this, this is uh, describing this. Okay, so this is describing how our parameters have to be updated. So sector here is meaning the previous stages parameters. During the training, we have multiple iteration. So this sector is describing previous iterations parameter sector. And we are adding something to previous parameter to get the new parameter sector. Okay, we iteratively do this to update the parameters of the architecture. So similarly, the babies, I mentioned that babies are getting some feedbacks from the parent iteratively, right? Spending some time by getting feedbacks iteratively, they are getting smarter, right? By improving their parameters of brains, right? Similarly, the deep learning architectures are getting smarter, becoming to have more information about the tasks that we are intending, getting feedbacks. You can see this term as the feedback, okay? And adding that to their initial parameters, okay? And what this DL dissector means, you have to understand this, okay? And so you somehow, from now on, have to understand what these subsequent layers are also doing, okay? This is the final deep learning architecture, okay? But we add one more layers to the final deep learning architecture and actually wanting to calculate some loss function. Okay, loss is meaning that the difference between ground truth and the network's prediction. Okay, so in ideal situation, our network have to how to say how our network have to predict the ground truth. Okay, so in ideal case, the loss should become zero. Okay, right? So our goal is making loss close to zero, which means we always want to minimize the loss L. Okay, we always want to minimize loss L. And actually, if we differentiate the loss L respect to the parameter sector, which means parameters of all the layers, okay, in the deep learning architecture. So so this term DL dissector is actually having the direction that can minimize the loss L. Okay. So how to say? mm, I yeah want to draw some graph here. So y is the loss L, and x, we can denote it as the parameter. Of course, this sector is some vector. So even though I draw it like the 2D graph, in the reality, it is I mean, you have to, in fact, have to draw it in the multi dimensions, okay? Because the sector is vector. But for the simplicity, I'm drawing it like in the 2D graph, okay? The important thing here is because all the networks, okay, all the networks, deep learning networks, and also even the functions that calculate the final prediction y with somehow here the ground truths are inputted. Okay, so normally the loss function is measuring the ground truths and their distances using the Euclidean distance or some other functions. Okay, you can interpret that layer, that calculation as the another layer, differentiable layers, because the loss L is differentiable respect to this y, and also yeah, because I mean, because the final loss L is calculated through some differentiable formula. So the final loss L is differentiable respect to their y, okay, the input. So we can interpret this last calculation that can calculate the loss L also as the layer, okay? So if we interpret the last part as the layer, the good thing is the loss L could be calculated from the intermediate parameter sector of all the layers. So somehow we can parameterize the final loss L respect to the parameter sector. And because of that, we can calculate this DL sector, which is the how to say the direction that can minimize the loss L. Okay. So when given this function, for example, let's say the simplest case, okay, and if the graph of L is like this, the minimum loss L is happening here, this part. And let's say our initial parameters are located here, okay? Then the next parameter have to be, how to say, move to this direction gradually. And eventually, it have to achieve this, I mean, global minima, okay? Uh, Anyways, in this part, you have to notice that this DLD sector is denoting the direction where we can minimize the loss L. Okay, so this is denoting the direction of sector that can minimize the loss, and also we multiply very small scale scalar value. Okay, normally we choose it like 0.1 or even smaller values like this is selected, and we multiply very small scale value to this direction and update parameter sector for that direction because that is the direction that can minimize the loss. Okay, and that becomes the new parameter sector. And in the next turn, we again do this until it reaches the global minimum. Okay. Okay. So this is similar to what babies do. Okay. They are gradually learn by giving some feedbacks from their parent. And this loss L is somehow you can see, interpret that as some feedback that is calculating the distance between ground truth and the network's prediction. And by seeing that, you know where to update our brain's parameters, network's parameters. Okay. And in that direction, we indeed update the parameter gradually. And by doing that, the network parameters are getting smarter and smarter. Okay. And that could be done only when you can calculate this DL dissector, right? And this DL dissector can be calculated when all the layers inside the entire deep architectures are having these two gradient, okay, which means all the layers inside the deep learning architecture have to be differentiable, okay, respect to their output, to the initial input, and also respect to their parameters, okay. Okay. And sometimes it is not that simple to calculate the gradient value when deep learning inside the deep learning architectures. So, I mean, when given just one, how to say, one layer, if we know the y is, for example, multiplying 2 to the initial input, okay, then we can directly calculate their closed form solutions like S2, right? Okay, we can easily calculate this, okay? But in the when the multiple layers are combined, for example, if we know the forward functions of this H and also forward functions of this F, but calculating them together and having more by stacking more layers is becoming not simple, okay? And also achieving that in the PC computer is also not simple. So I will show how we can achieve them step by step manner, okay? So for example, here, X and Y, Z, those are input to the deep learning architecture. And this F is the final output of the deep learning layers. So we are having two layers here, right? So the Q here is the intermediate layer which can be calculated by combining X and Y with operator plus, okay? And also here, the operator multiplication is also combining Q and Z, okay? So the F is, you can interpret that as this, okay? This is the forward rule, okay, of this deep learning layer, okay? And I will show how they can calculate the differentiation of the final layer respect to each node, okay? So, when given arbitrary deep learning layers, using this step-by-step calculation, you can find differentiation of final layer respect to all the node inside the deep layers. Okay, and if you can calculate this, that could be used for calculating DL dissector for entire deep learning networks, okay? And using that technique, step-by-step calculation technique, you can get this DL dissector and update any parameters inside the deep networks, okay? So this type of rule is important. And actually, we call that as the backpropagation algorithm, okay? So you may heard about the backpropagation algorithm. We first calculate the forward rule, this, and then calculate the differentiation of the final node respect to each intermediate node, okay, using this step-by-step approach. And that step-by-step approach is called a backpropagation algorithm, okay? And in that backpropagation algorithm, we first calculate the gradient for node that is closest to the final node, okay? And now we see this formula. So this is the intermediate node Q, and this is the Z, and they are combined via the multiplication, okay, to output the F, okay? And this -2, the green values, are the input values, okay? So -2, 5, when they are added, 3 comes out here, right? And -4 was initial value for the Z, node G, okay? And if they are combined via multiplication, the final value in the F will be -12, okay? This is simple. The fourth rule is simple. That is the simple basic calculation, okay? But in the reverse way, we have to calculate their gradient, okay? And the initial gradient at the final node is always 1. So you can interpret it as this. df, differentiation of final node f respect to the final node. That is always 1, okay? The differentiation of itself is also 1, always 1. And also here, what should be there is the differentiation of final node f respect to node q have to be located here. And also we have to calculate differentiation of final node respect to node z, okay? And I will rewrite the formula here, okay? And I will now calculate the values. So when calculating, now I will calculate dq df, df dq first. So for calculating this df dq, I have to apply d dq to f. Okay, are you guys understanding this? So for calculating this, for each side, I will apply d dq. Then this will become this, okay? The right side will become df dq, right? And then if I apply d dq to this, then that will be the value, okay? And also q is variable, but you have to notice that z is constant in the, I mean, q side. When seeing through the q aspect, z is the constant, and their value is actually -4. Okay, initially z was -4, and q, when differentiating q, that we regard that as the variable. Okay, so when we apply d dq for -4q, then this becomes just 1, okay? And I mean, I will say it like this. If this is constant, it could be first out, go outside of this parenthesis, okay? And it becomes like this, and it eventually becomes just -4, right? Okay. So which means df dq is -4, okay? And also we can do same thing for this node, okay? We can apply d dz for both sides of this formula. Okay. And we can regard this as constant now, and that value is 3. Okay. So now it becomes like it disappeared. I don't know. Okay. Anyways, oh, okay. Uh, it's now becoming like, okay, and oh, this part it simply goes to 3. I don't know why. Okay. Anyways, um, sorry. We have to apply uh, this, and it becomes like this, and it simply goes to 3. So that's why we can calculate dfdz as 3. Okay, are you guys following this? And also we have to calculate this 2, and this will be the differentiation of final node respect to the x. And also here we can calculate also dy df and df dx. Okay. Okay. Mm. Okay. Um, okay. And also, when calculating this df dy, what we will further do is df dy would be via chain rule. I don't know why this is continuously disappearing. I don't know. Okay. df dq multiplied by dq dy. Okay. Are you guys finding this? Okay. The differentiation of final node respect to the initial y will be the multiplication of the differentiation of f respect to the intermediate layer at q. Okay. And also this will be the differentiation of intermediate layers output q respect to the y. Okay. We already calculate this as -4 here, right? And the thing we have to further calculate is dq dy. Okay. And dq dy, for calculating dq dy, we can use this formula. Okay. When adding x and y, we can calculate q. Okay. And for calculating dq dy, we can apply d dy to both sides. Okay? So dq dy will be 0 plus 1. Okay, are you guys understanding this? So when differentiating x respect to y, okay. When differentiation of x, differentiating x respect to y, it becomes simply 0 because this is constant in the aspect of y. So we simply make it 0. And this is variable, okay, having power of 1. So it becomes, their gradient becomes 1, okay? So dq dy is simply goes to 1, okay? And so here we have to calculate df dy, which is the multiplication of df dq and dq dy. And this was -4, and this is 1. So it becomes -4, okay? And also here, their we have to calculate df dq, df dx. And this is again the multiplication of dq, df dq, and dq dx. And dq dx is also 1. Okay, so that's why this notice df dx becomes the -4. Okay. And actually, this calculation, you can understand backpropagation algorithm, how the inside the computer, there, I mean, when deep learning architectures are stacked, how their intermediate gradient can be calculated. You can understand that. Okay. So using this, for all the intermediate node of the deep architecture, you can calculate DL dissector, okay, via the chain rule. And if all the layers inside the entire deep architectures are differentiable, which means you can calculate these two gradient for each layer, the entire layers, you can calculate DL dissector and can apply gradient descent formula to update parameters, okay, to make it smarter using the feedbacks from the data, okay? And I mean, during quiz, I normally raise some problem using this calculation, okay? And I want you to be familiar to this calculation, okay? Okay. So in CNNs, any differentiable layers could be located here, right? So I mean, from the RGB array and to map the RGB array to the one-dimensional probability vector that is describing probability for each class, we can have some arbitrary operations which is differentiable, okay, which we can constitute any possible layers if those operations are differentiable. But thing is, so I mean, you can find different types of deep learning architectures, but CNNs, that is one of the successful deep learning architecture. That is using actually the convolutional operation. Okay, the C denote the convolution operation. This convolution operation was the operation that is used for image filtering. Okay, so I mean, uh, if you are familiar to using the Photoshop, there are many filter, right? There are sharpening filter and blurring filter and any other filters that is corresponding to any effect. Okay. So this convolution, if you take the signal processing class, the convolution operation can actually transform the input signals to have some other characteristics. Okay, so this convolution operation is widely used before for processing the image signals before. Okay, so before deep learning, the convolution was widely used to process the images to reduce their noise or sharpening or other to give other effect on the image. Various filters were used. And also, so it means convolution is one of the successful operation to process the image signals. Okay. At the same time, it is differentiable operation, which means, I mean, the only characteristic that I mentioned was for differentiability is their output have to be differentiable respect to their input, and their output have to be differentiable respect to their intermediate parameters, right? If, how to say, if that layer's formula is polynomial, if their intermediate layers operator is composed of plus, sorry, plus multiplication and subtraction and sum of divisions, okay? If those operators are used, that is actually composing these polynomials, okay, when making the output using these four types of operator, that would be polynomial, right? And every polynomials we can get different, we can calculate their gradient, okay? Okay, so, and also convolutions, if you think about their actual operation, that is composed of multiplication and additions only, okay? And because of that, convolutions are differentiable operator, okay? So in the middle, every layers are having the mostly multiplication and addition to get the output. So because of that, we can get these two gradient easily for the CNN architectures. And it means the entire CNN architectures are differentiable. So we can apply gradient descent algorithm to update their parameters. Okay, even though they are very huge, we can iteratively and repetitively apply the gradient descent algorithm to update their all the intermediate parameters. Okay, are you guys understanding this? Okay, and I mean, yeah, I mean, this is more fundamental characteristic, differentiable. Okay, uh, any differentiable layers could be here, but CNN convolution operation, that is also very effective operator for processing the signals, especially one-dimensional and two-dimensional signals. So, I mean, that was the reason why maybe the CNNs could be one of the successful deep learning algorithms. Okay, and inside these CNN algorithms, these layers are differentiable. All the layers inside the CNNs, those are differentiable because they are mainly composed of plus minus I mean multiplication and division operator, right? And their main operation is convolution operation and pooling operation, and also the fully connected operation. And we will see those algorithms in detail level in the later sections, okay, later slides, okay. So we will see that in next Monday, okay. Sorry about this continuous delays for today's slide, okay. But maybe next time there will be no issues like that, okay. Anyways, the important message here is the differentiability today. Okay, I believe that you can follow that. Okay, okay, thank you and see you next Monday. Okay, thank you.